with a focus in AI and machine learning, applying it within the defense realm, particularly in regards to radar. So that's my focus for my career field. For what I'll be talking about today, step away from the speakers for a little. So I'll be just giving a brief overview of what robotics is, and especially for the youth crowd who doesn't know quite what is involved in robotics. I hope you find this informative. For those who are more advanced in the engineering fields, I'll be talking a little bit about my personal experience in industry working on robotics. And some of the modern areas that are being researched for robotics. And especially if anyone has real professional experience in the field with robotics, I'd be happy to interface with you and network with you as well. So I'll be talking through some of my experience and then some tips also for the youth if you're interested in robotics. So what robotics is, it is the intersection of science, engineering, and technology, and you produce machines that are called robots, and they have different kinds of capabilities, and I'll talk about that in a minute. And they can help to replicate or substitute human actions. They can often do repetitive tasks without wearing down or without fatigue. So oftentimes you might have in the industry kind of like repetitive stress syndrome that happens when workers are doing the same kind of mechanical actions. When you replace those actions with robots, now you no longer have that kind of fatigue. They can do it as many times as possible, as long as the hardware lasts. And they can oftentimes do it with higher precision and accuracy. So robotic surgery is becoming very popular these days, where when it comes to performing surgery, precision is really required, right? It's important not to make mistakes, and so being able to do that with robotics is becoming more and more of a research area these days, especially in countries like Germany. Robotic surgery is becoming very cutting edge. And robotics is also like multidisciplinary, so it combines mechanical, electrical, and software engineering disciplines all together. So that's why it oftentimes is very exciting. For instance, when I think back to my college days at the college fair, our robotics club table was oftentimes very much a center of attention. Students would be flocking to the robotics table to see what was going on and to be able to get a chance to interact with the robots. Next slide. So some of the components of robotic systems. What does a robot consist of? So a robot consists of some kind of mechanical structure. This allows it to be able to move around in the environment and to be able to apply forces to interact with the environment. So sometimes you need to grab items, you need to pick them up and move them from place to place. The robot itself needs to move around, and so it will have wheels, it'll have a structure, and it'll have a particular shape to suit the needs of the goal for the robot. It will also have some kind of perception system, so it'll have a collection of sensors that helps it to do its job. So whether that's touch sensors, capacity sensors for things like water levels, there's many kinds of sensors that you can have. Light sensors, infrared sensors, LiDAR, which uses light in order to detect range and distance, which is becoming very popular on autonomous vehicles, autonomous cars. And you'll have a decision and control system. So this manages all of the sensor inputs and creates decisions and actions, and based on a feedback loop in order to achieve the goal in the environment. So some of the modern focuses of robotics is aerial robotics. It's becoming very popular. You have a lot of UAVs, a lot of drones that are being used these days. Amazon is trying to move towards the scheme of UAV delivery, like drop shipping of packages. It's becoming very popular in countries like UK, where they're doing a lot of testing there. It also has, there's modern aspects to perception. So LiDAR sensors actually didn't exist more than a few decades ago. So it's really recently that LiDAR technology is becoming more advanced to be able to allow for autonomous vehicles to have the sensors all built in. LiDAR used to be like very big, very cumbersome, and not suitable for portable technologies. And now with recent advances, it's becoming smaller and smaller scale, so that you can hold LiDAR sensors in the palm of your hand. And those same sensors can provide 3D imagery just by doing scans of what's in front of you. So perception is also becoming more advanced. Navigation and motion planning, this has become increasingly more commonplace, and the example that I think a lot of you will relate to is robotic vacuums. So robotic vacuums, back in the day, if you remember some of the initial generations of robotic vacuums, they used to bounce all over the place, like like those old icons on the DVD players that you would watch bounce around on your screen. The robots themselves were kind of bouncing around like that. The idea being that if you bounce around enough times, you'll cover the entire square footage of your house. Since then, by adding additional sensors, additional motion planning or navigation planning, your robot is able to smartly figure out exactly where in your house it is. It's able to map your house for you and able to avoid obstacles. So all of that like navigation advancement you're seeing in your own homes, even with the robotic vacuums that you own. There's an aspect of this that you would study in industry called inverse kinematics. So for instance, when you have a robotic arm and you're trying to have it move from one place to the other, when you kind of think about like traditional robotics, you program a movement and then you see where the robot ends up and then you decide what the next action to take is. So you're kind of thinking in forward kinematics, like you apply a signal, the robot moves, then you figure out, okay, what do I need to do next? Then you apply another signal. Inverse kinematics starts out with the endpoint, and you do the reverse engineering of, to get to this endpoint, what do my joint positions for my robot need to be? So you do a backwards calculation for each endpoint, and by doing so, you can even do so in a simulated manner, and you can plan for the robot to do an entire sequence of motions just using the mathematics of where the joints need to be. And so you can program that in that fashion, and there's a mathematics study that you can do for inverse kinematics. And then you have advanced sensors. Camera sensors today versus 20 years ago are much more advanced. You get much more resolution. LiDAR, as I mentioned, has come a long way. And so sensors are also increasing in their capabilities as well. So just talking to some of my experience having gotten acquainted with robotics, technically my field or my domain at my workplace wasn't always focused on robotics, but I did have some industry experience, and I'll talk to that. But what really got me interested in robotics in the first place, which I hope will be true for a lot of the youth here, especially having parents who are in the STEM field, I would hope that you would get some kind of exposure during your schooling, which is what encouraged me to go into the field of engineering. And so during high school, one of the first challenges that I did was called the US First Tech Challenge. And so FTC is targeted towards high school students. I believe 8th graders can join now as well. So it's 8th to 12th grade domain. And you basically, there's a bigger version of this called the US First Robotics competition. So that one is really big scale, like 2 foot by 2 foot, 3 foot by 3 foot by 3 foot robots. We're like really big robots. But the FTC is kind of like the mid-range, so 18 inches cube. You form a robot, and it's meant to compete against other schools to complete certain challenges, and the challenge changes every year. So this helps to teach you C, and recently they've moved to Java programming. So this gives you real experience with programming that you would use in industry. It teaches you the mechanical engineering concepts, so you'll have to deal with gears, applying torque forces, connecting the metal structures in order to achieve your goal. And you'll also learn the electronics and the wiring and the programming all associated together. Then in college, I had the experience of being able to lead our college robotics club. So I was the president for about 2 years in college. And so during my undergraduate years, we were using things like Lego Mindstorms. We were using Vex robotics. We had some parts from US First. And so we're doing many things with these kinds of different robotics to be able to encourage and especially do outreach for teaching students that, hey, like you can learn this no matter what level you are. You can get accustomed to learning robotics and really enter it into the field as increasing in your technical skills. So if you go to the next slide, I think I have one of the one of the videos. This is a video, okay, here we go. So this is a video, for instance, of a LEGO Mindstorms robot that is able to solve a Rubik's Cube. So this is one of the robots that we also had at our college that we had set up, and this attracted a lot of attention. Like I was saying, when we had club fairs, students would be flocking to see like, oh, what's going on here? And so what it does is it uses the color sensor and the different motors that it has in order to read the colors from each surface of the cube. It does the calculations internally, and then it performs the motions to change the different faces of the cube in order to solve it. So that's all automated. And this is an easy way to kind of like introduce students to robotics. Some of the, if you go back, so some of the work that I've done for church also is that occasionally the folks from our church, when we're doing different kinds of plays, will have these very grand ideas of what can be achieved using some like clever tricks, some creativity, and sometimes some robotics and engineering skills. So in particular, I really thrive on being able to provide robotic solutions for some of the church props that we use in these kind of plays. And so one such play that we had done was based on St. George, who's our patron saint for our church, named after St. George. And so we had done a St. George play where there was a request to have a dragon that had these different kinds of capabilities. So they wanted the dragon to be able to flap its wings to open its jaw. I had added a feature to like move the tail. When the wing was disconnected, they wanted it to spray blood out. So these were the kinds of different requirements that were given to me, and I was able to kind of produce this picture dragon that you see here. We had suspended it on a paracord, sure enough, like when the wing was disconnected, it would spray this like red fluid using a pump that was inside. I had a microcontroller that was kind of managing and controlling all this. There were servo motors that were kind of producing all the movement. So being able to do these kinds of works for church was very encouraging and a very cool use of my skill for church to be able to do this. And so then that encouraged me to kind of make a 2.0 to kind of build on that. And so that's the scale model that I do have with me. I can show in the back at least a video of it working. Unfortunately, just missing the exact cable that I needed to reprogram it. But otherwise, you would be able to see it kind of moving its jaw, flapping its wings, and moving the tail in a realistic manner. It can rotate its neck as well. And so I do have an instructables page, actually. You can find it online. If you search how to build an animatronic dragon model, you'll find my article that I wrote 4 years ago, just detailing how any individual can kind of come up with any creative project, and you sketch it out, you kind of create those engineering prototypes, and you build up to the final product. So next slide. Oh, yeah. So this is the actual dragon model. So just to show you the kind of scale. The actual one, I would say, was maybe 10 times, maybe 4 to 6 times bigger than this. But this is the scale model. So it uses the different servos, the servo drivers, in order to control the different logic. So this is a project that I would say like even the high schoolers can dive into and work to create. When you start out initially, it may be easy to move the individual servos one at a time in sequence. When you get more advanced with your programming, you can do everything in parallel, and there's smart ways to do that. Some of the robotics work that I've done with Sikorsky. So Sikorsky is a company that is now owned by Lockheed Martin. And as part of my engineering rotations I was doing through a leadership program, I had the opportunity to take about 9 months of a rotation at the Sikorsky headquarters in Connecticut, near Shelton area. So at that facility, there's like lines of assembly of the different helicopters. So the Black Hawk helicopters, the King Stallion helicopters, the Marine heavy lift helicopters that you see pictured here. They're really big, they can fit 50 people in them. But there's a lot of work that goes into engineering the helicopter parts. And we're talking like parts anywhere from like something that can fit between your two hands to something that's like twice as tall as you are. So like a really drastic variety of parts that are engineered and manufactured in the facility, and they take everything from start to finish in this particular plant. And so one of the applications of robotics, on the next slide, you'll see some of the industrial robotic arms that are used on site. So there was a Kawasaki robot on the left that was used for sanding different composite materials that are used for the helicopters. Composite helps the helicopters to fly lighter than using metal in some cases. And then there's a Fanuc robot, the yellow one on the right, that was also used for deburring of metal parts. And on the next slide, you'll see a video of how you can actually simulate the robotic movements completely programmatically on your laptop. You can actually bring in the CAD model of the part and trace the contour that you want the robot to follow. You can verify in simulation that it's going to do what you want it to do. And then you'll kind of see, like, once the contours have been traced, you'll actually see the computer calculate the joint movements needed, like I was mentioning before, right? It all comes down to the joint movements of the robot, and it will feed those joint movements and figure out how to precisely move the robot at the right angles, at the right positions with exact precision in order to deburr the parts, which really means like smoothing the edges of the parts. And some of these parts are super complex, so this can be really hard and tedious for a human to do repetitively, but it can be very easy to program a robot to do so in a safe manner. On the next slide, you'll see a kind of example. So this is like translating that program, those sequence of joint movements, to the actual robot. So in this circumstance, you kind of have the teeth of a very complex gear. And so this is what the CAD model looks like. And so you'll see the robot is actually going to trace the edges of that because it was programmed to do so using the same technique. So it's actually deburring, it's smoothing the edges of this metal part by going around with that exact precision because it was programmed that way. Next slide. There's also a segment in Sikorsky where they're starting to get into collaborative robotics, or cobots, and this is also becoming a trend now. Instead of taking up huge surface areas in your factories with these complex robots that can be dangerous, and you certainly have to go through a lot of safety rigor and risk assessment with these large robots, because if they happen to swing into you, if they're a very large robot, they're moving very fast, they're very heavy, they can injure a person. So collaborative robots focuses on robots that can still perform your tasks at different levels, different power levels, but they can work alongside humans in a safer manner. So what happens is anytime they detect that there's a force against them, it's the assumption that there might be a person there, a person's arm, it kind of like bumps into the robot, and they have sensors to automatically shut down and stop the robot when this occurs. So they can collaboratively do movements in a closer space, but in a safer manner. So this is the universal robotics arm that you see pictured here on a power kind of like conveyor belt. And so it can move up and down the conveyor belt and also rotate its arm using 7 degrees of freedom. It can really move around and do any kind of tooling that you need it to do. Next slide. Here's another project that I've worked on while I was on my engineering rotations. The first year they have you do this robotics project collaboratively as a team with your teammates. So this was a robotic arm. This was the third of the 3 robots I was hoping to demo today, but unfortunately couldn't find the plastic parts and I couldn't 3D print them in time. But this particular robot, I had 3D printed the different parts that you see, the red and the purple parts that you see, in order to, like, the challenge was to go around a baseball field and collect these eggs. It was kind of mimicking soldier retrieval in the field, in the defense field. And so it would go around and collect these eggs. And so this was the arm portion that we were demonstrating here. It uses remote controls. It has suction cups on the ends, which we found better than like some of the pressure sensors that we tested. The suction cups actually mechanically prevented the egg from breaking when we went to grab it. So it was kind of like a mechanical touch that we implemented here. And it's able to pick up the egg. It has 6 servos that it's using in order to achieve this. It can rotate its base. It has multiple degrees of freedom with the different arm segments, and it's able to drop the eggs into the carrier there. Next slide. So the future of robotics, it's definitely getting very advanced. Some of you might recognize the Optimus robot that's being made by Tesla. And so, different advancements are coming in terms of LiDAR, like I mentioned. Camera sensors are becoming more and more high resolution, allows for better computer vision. Tactile force sensors, like what Optimus is doing here, it's using the tactile force sensors to detect precisely how much force is being applied to the different fingers as it performs different tasks. Nanotechnology is also becoming like increasing trend. It's becoming very advanced as well. You have more research into advanced robotics that can enter the bloodstream and can perform specific tasks for medical purposes. And in terms of robotics, as was mentioned before by previous speakers, AI and machine learning, which is my field of expertise, is becoming increasingly applied in robotics as well. So you have, one of the main focuses, aside from computer vision, which is advanced detection of different objects that you would see, like you see in autonomous vehicles, you also have generalization of tasks. And what that means is, like, it used to take maybe days or months for a programmer to sit and teach a robot how to do an exact task. And now, using the power of AI, you can generalize that robot, so you can teach it how to do a series of tasks and essentially teach it how to learn by just one observation. And now, even without sitting to program it to do multiple things, you can teach it how to do any number of tasks. So you program it once and teach it to learn, in essence. And you can say, okay, like, watch me like crack this egg. You'll give it like one video, one demonstration of what it looks like to crack an egg into a bowl for cooking. And it will be able to repeat you right away within seconds without any further reprogramming. So that's kind of like generalization. Then you can take that same robot and teach it how to slice vegetables, and it will do so like immediately, without any kind of delay, without any kind of reprogramming. So that's kind of where the field is headed to in terms of generalization using the power of AI. And so you'll see increasing utility in robotics going forward in the future. So just to wrap up, some final tips for robotics focus for students. If robotics interests you, if anything I mentioned kind of makes you think like, oh, I'd like to be able to see how that works or dive deeper into making a robot, some of the tips I can give you is for college majors, what you might be interested in is mechanical engineering, which will really give you that background into the forces needed in order to build a robot. Electrical and computer engineering, which will give you the circuitry background in order to build the sensors, and computer science in order to learn the programming, because it really takes advanced programming to be able to achieve the more complex tasks these days. Some of the extracurriculars that you can do, even as early as high school or even middle school, is getting involved in any college or any school robotics clubs that you have at your campus. So that's using LEGO Mindstorms, if you have US First or VexU competitions, and you have clubs that facilitate going to those competitions, highly encourage you to sign up for those, because those can really help you to get real-world, first-hand experience dealing with these physical robots. And I highly encourage you to build a project from scratch. So just like I was able to detail on the Instructables page for creating this animatronic dragon, you can look at many tutorials online on how to purchase the core components and assemble it into the project of your dreams, whether it's animatronics, whether it's a surgery robot, a robotic arm, an underwater robot. There's so many tutorials out there that can help you get started. And building it from scratch is really beneficial to put on your resume because it shows recruiters at colleges, at workplace, that you know how to take a project under your responsibility and really take it from start to finish. So it really shows a lot of leadership and core technology skills. That's pretty much it. So I'll be able to demo one of the robots that I do have is a small reprogrammable robot. It's called an Edison robot, and we're using it this year for the mentoring of the high school students that we do in the spring. So it's easily reprogrammable. I'll be able to show you how it can follow a line very easily, actually using one block in the graphical interface that you use to program it, but you can program it in a variety of different ways, and I'll show you exactly how that looks in the back. Again, apologies that the dragon wasn't working today, but I'll be able to show you a video of what it does when it is functioning too. Thank you very much.
Justin, raise your hands. I am. And I'm going to tickle my brains a bit, but Justin, where are you, Justin? Yeah. Justin, weren't you one of our talkers before? Yes. So I do remember him from many years ago. He did give a talk to us, and that was, I don't know, at least 6 or 7 years ago, and I'm so proud to see him come back, and definitely very inspired to see the next generation really come up into more advanced forms of engineering, which we never had access to. But thank you for inspiring our children and the next generation into this field. Robotics, and I work with healthcare, so I know when we design the rooms for certain doctors, they tell about robotics arms, the precision of how it needs to be, and the amount of wiring we need to do just to get this thing functional. So it is very, it's very interesting to hear the back end of it. And also for the youngsters here who have come today, who are looking into engineering, definitely this should be an inspiration for you to get into programming, robotics clubs. And I would also like to ask if is there any youths who have any questions out here to ask Justin? Please come forward to him. He's very approachable. Come and get some guidance from him. And may I ask, why is it called the Edison robot?
It's definitely inspired by Thomas Edison, who was one of the inspirers for engineers.
So it was inspired by Thomas, because it was inspired from Thomas Edison. That's what Justin says. So please keep your minds open to it. The next generation, you know, that's what's coming up in the near future. Now moving on to the next program, we'll just lighten it up a bit. We'll have a solo by Mrs. Lakshmi Shankar. Yeah, she'll have a solo by her.